All right, Workplace 20 fans, welcome to 1.3 Rate of Change. This is the last section in our unit, and it kind of brings things together, and there's a lot of good information here. So let's get started. All right, so the first term that we're going to look at is rate of change. All right, and rate of change, if we look at it, all right, rate of change is the rate at which one variable changes compared to another variable, which is good to know. So a good example of that, what I would say is, like, say you have a variable of money, and how does that change compared to the variable of hours? So basically thinking of, what wage are you making per hour? All right. The next word that we have here is dependent variable. So when we look at the notes here, dependent variable is a variable whose value relies. That's the key word right there, because it's dependent. So if you depend on something, you rely on it. It relies on the value of another variable. So when we go back here and look, all right, and just to kind of clarify and give you some hints on that, your dependent variable is always going to be your y-axis. Okay, it's going to be your rise. That's what your dependent variable is going to be. And for example, when we looked at rate of change, that could be, in this case, would be something like money. Your money is going to depend on how much time you work. So that leads into our next term, independent variable, which when we look here, independent variable is a variable whose value can be freely chosen, which is not dependent on any other value. So that again would be like time, like hours, right? So your independent variable is always going to be your x-axis, okay, which is, axis. Let me make sure I spell that right for you watching out there. X-axis, and that's going to be your run. So that would be like hours. And another thing you can think of on here, this is going to be your vertical, and this is going to be your horizontal. So hopefully you're making some really strong connections, and that's what math is all about, making connections, understanding that your y-axis is your rise, is your vertical, your horizontal is your x-axis. When I said horizontal, right? So all those play in together. And if you can understand that, it really makes this a lot easier. So when we just scroll down a little bit here, the graph of a linear equation is always a straight line. Okay, so we have examples here. Here's a straight line, here's a straight line, here's a straight line, and here's a straight line. So those are all examples of linear relations. Now we will explore these more as we move on, but you can see here this is going to be, as you go from left to right, this is going to have a positive slope, and you go from left to right and you go down, you're going to have a negative slope. This one's really special. You don't have a run, right? You just have a vertical line. So when you have a vertical line, right here, you have an undefined slope. All right, where here you have a horizontal line. Horizontal, sorry about that. And with this, you can see here that you have a run, but you don't have a rise. So this here, your slope would be 0. And we'll explore this more, especially when we get into building our Minecraft roller coasters, where I'm going to ask you to develop positive slopes, horizontal slopes, negative slopes. You might go back over and then come straight down and do a vertical slope and understand how that looks and put it all together. So I'm excited about that for you guys, and that plays into rate of change quite a bit. So let's take a look at an example here. We've got our friend Ken, and we have our friend Bob, and they're both delivery truck drivers. All right. So the first piece of information here with Ken is, that he gets paid $20 an hour. Okay. Now in my previous example, I was saying, like, here you can see that the money will be your dependent variable, so that's going to go on your y-axis, and an hour would be time, so that's going to be your independent variable, and that's going to go on your y-axis. So we'll come back to that in a bit. And we'll look at Bob. Bob gets paid $16 an hour, but he also gets $20 for a gas allowance. which is good, and it will make sense in a bit why that's really important information. So we'll go back to Ken, and we'll do Ken in red, and what we'll input here, so our independent variable was our time, and our dependent variable would definitely be our money. So if Ken works 1 hour, right, he would make $20. If he works $2, he would make $30. And if he work 3 hours, he would, oh, wow, I made a mistake there. Let's erase that. That doesn't make sense, does it? All right, if he worked 2 hours, he would make $40. That's better. And if he worked 3 hours, he would make $60. All right, when we take a look at our friend over here, Bob, Bob's a little bit interesting because even though he makes $16 an hour, in that first hour, he would have made $36. Well, how did he make $36 if he's getting paid $16 an hour? This piece of information here was critical. And when you see the word plus, plus means to add. So no matter what, Bob's going to get that $20, whether he drives for 1 hour or 50 hours. So that's why I added the $20 rate to the 16 an hour. So that first hour he makes 36. So in a second hour, again, we would have to add 16 to that, and that would give us 52. And if we add another hour onto him, we'd add another $16, and he'd be at 68. So you can see here jumps $20, jumps $20. And we can see here jumps $16, jumps $16. So that's where we get a linear relation from, because it has that constant rate of change. All right. So who makes more money after 2 hours of work? Much more. So if we look at that, you can see that our friend Bob after 2 hours, that's Ken, after 2 hours makes 40, and our friend Bob makes 52. So 52, and we're going to subtract 40, that gives you 12. So who makes more after 2 hours? It's definitely going to be Bob, and he's going to make $12 more in that time frame. So if you've noticed and you went back to the question, you can see that actually Ken gets paid more per hour than Bob. So eventually Ken's going to make some more money than that, because eventually Ken's going to make up for that $20 in gas allowance. Now we need to figure out when that would happen. So if we go back, remember we had our friend Ken, he rate 1 hour $20, 2 hours 40, and you can see here we're going at the same rate, right? There's your rate of change. So 5, he's making 100, 6, 120, and hopefully my hand's steady there, and you can kind of see the linear relation of what Ken makes. If we take a look at Bob, Bob's going to start at 20 right off the bat, right? So after an hour, he's going to make $36, right? After 2 hours, he's going to make $52. So we'll kind of have to try to figure out what that works. After 3 hours, he's going to be making about 68. After 4 hours, he's going to be making about 84. And then after 5 hours, there we go. We can hopefully put that line. That's when they would make the same of money. After 5 hours, they both be making $100. After that, Ken will make more money than Bob. Another way to do that, we did that graphically. Another way is through, we'll do this. We'll calculate Ken and Bob's rate of earnings and write an equation for each relationship. So again, if you wanted to know how much money, right, that Bob makes, we'll start with Bob because I got the blue going here. He's going to make $16 an hour, right? So 16 times X. X would be his hour. I could put T in there too. Actually, you know what? I'll put the T to keep it consistent with what we had before. It doesn't really matter what you put in for variables, plus that $20. Remember, that came from his gas allowance. So that would be Bob's rate of change, right? That would be his equation. And our friend Ken, right, how much money he made, he would go 20 times the time he did. Okay, so if you put 5 in here, right, you see that 5 times 16 gives you 80. 80 plus 20 gives you 100, right? And if you put 5 in here, 20 times 5 gives you 100. So that's when they would make the same. Another way to do this equation to see how they did, so you have both iterations, this is a little extra bonus work here. To figure out when they'd make the same, you would have to make these equations equal to each other. All right, so these statements equal to each other. And again, the way you would do this is a two-step equation, which goes back. Hopefully you learned this in grade 9 math and before. If not, hopefully this is a nice little reminder for you. I decided to subtract 16t from both sides because 16t minus 16t cancels and gives you 0. So you're left with 20. And because you have t's, you can do that. You can combine them or subtract them. You got 20t minus 16t, which gives you 4t, right? And you want to find out what t is. That's 4 times t. The opposite of timesing by t is dividing by, the opposite of timesing 4 times t is to divide by 4. Hopefully that makes sense. So I'm going to divide both sides by 4. 4 divided by 4 is 1, so I'm left with t. And 20 divided by 4 is 5. So there's a couple of ways to figure out, when they would make the same amount of money. And you can see the equations that are made. All right. That was fun. I enjoyed that. Like, it's interesting to put it together like that and see how they all relate. So you have tables, you have graphs, you have equations, and they all interwork together. And I'm hoping that will really make sense to you guys. All right. One thing you can also do is you can use points on the line to calculate what slope is, right? Before we talked about in our notes, the delta, the change, right, in your vertical over the change in your horizontal, right, that would give you slope. So one way to be able to do this is by using your lines. There's a formula that you'll be able to use, and basically it's using these coordinates in here to find out what the change here is on your horizontal and on your vertical. So remember, you have a set of ordered pairs. Your x comes first and your y comes second. All right, your x would be your horizontal, right? That's your x, and your y is going to be your vertical. So when you look at this, your formula that you're going to do here is going to be y2 minus y1. Now what that's saying is that I'm looking at both these points on a line and I'm saying, okay, this y2 subtract this y1 would tell me the difference here of how far we went up, right, or your rise. And on the conversely, with your run, you'd have x2 minus x1, and that would tell you how much you changed here on your x. So when you look at something like this, and it gives you 1 point here on A at 4, 12, I would know that my x here is 4 and my y is 12. On that same line to get to B, right, you can see here that 14 would be my x and 28 would be my y. Now where do these little 2's and 1's come from? Well, I'm going to pick this as x1. That's the first point on my line, and this is y1 because that's the y value for this first coordinates on this graph. Okay, here, because this is the second one, that's why this would be x2 and that would be y2. So now what you do is you would take your x2, sorry, we'll start with the y's. You got your y2, which would be 28, and you subtract from y1, which would be 12. All right, so that's our change in our vertical or our rise. And then you would look at your run. You take x2, which is 14, and you subtract that from x1, which is 4. 18 minus 12 is going to be 16, and 14 minus 4 is 10. So when you divide that, you get 10 divided by 16 gives you 1.6. So when it says what's the slope of that, you would be able to say 1.6. Now there's another little interesting part of this, and what's the length of the groove? Well, again, if you looked here, you would see that you have a right angle triangle. So if you wanted to know the length of the groove from here to here, you could use the Pythagorean theorem again to figure out that. You know that one leg, right, would be 16, right? That was our change from here to here. That, oh, sorry, I should say, well, that would be our change from here to here. That's our vertical, actually, sorry. So the vertical would be 16 from here to here, and the horizontal would be 10. And that's going to give us our hypotenuse. Remember, we have to square these because we're using the Pythagorean theorem. We bring up our calculator, right? And we go and clean this up. And we go 16 times 16, or you can hit 16 squared. Either one's fine. That's 256. So you put 256 here. 10 times 10 is 100. That equals the hypotenuse squared. This would be 356 equals the hypotenuse squared. Don't forget that squared. That's really important. You got to take the square root of both these sides. Let's go back to the calculator. And I will add my 100. So, oops. Well, I'll just cancel that. I'll go 356. Take my square root of that. So that's 18.6 equals the hypotenuse. All right. And it doesn't say again if it was inches or whether it was meters. So I would have to put units on there. So that's 18.6 units, all right, would be the length of the groove. So the slope is 1.6 and the length of the groove would be 18.6 units. Oh, I love it. Good times there, some good math going, and really hope that helps you understand and put things in together, and it's a good example. All right. Here's ones with different. You can do this. You can figure out. This is what we're talking about before. You can see here as you go down, what's happening? Well, that would definitely be a negative slope. When you see B, right, this also would be a negative slope. C, you could see, is a horizontal, so that would have a slope of 0. D has a positive slope, and E has a positive slope. And you could just take the coordinates to figure out your rise and your run, and what your slope is on that. All right. Well, I think is more than enough information to help you with this section. Again, reach out to me through emails, book up some time with me, reach out through the video for your flip grading, or you want to get hold of me and remind if you need some information. I would definitely like to help you out with that. All right. Thanks for listening, and have fun, people.